Salam, peace be upon you. My name is Muhammad Layak Siviki, the father of Holophase. Part 36. Generating Quantum Mechanics, Superposition, Measurement, and Entanglement in Phi. Remember the language we are learning. There is one field, Phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When Phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. We are now at the most delicate and profound frontier of synthesis of physics. Our journey through Episode 9 has been an expedition to understand the universe as a self-writing text. We've translated the Epic of Newton and the Symphony of Maxwell into dialects of our single phi language. We have seen how deterministic trajectories and crisp force fields emerge from the tapestry. But now we face the text's most enigmatic chapter. The chapter written not in bold, clear ink, but in shimmering, probabilistic script. The chapter where a thing can be in two places at once, where observation seems to collapse possibilities, where particles separated by galaxies whisper to each other instantly. This is the world of quantum mechanics. And our test today, in part 36, generating quantum mechanics, superposition, measurement, and entanglement in phi, is the most audacious yet, to show that this world of mystery is not a break from the phi grammar, but its most natural, inevitable expression when we read it with complete honesty. Our anchor image is a master scribe copying an ancient, fading manuscript. The original ink has bled. Some words are clear, others are smudged into overlapping possibilities. The scribe's job is not to invent a new story, but to faithfully transcribe all the information present in the smudges, the superposition of possible letters, the correlations between blurred words on different pages. He doesn't see mystery, he sees a richer, more nuanced text. Today, we are that scribe. Phi is the original manuscript, and the quantum wavefunction is our faithful transcription of its blurred, complex information. Here is the ultimate puzzle of this part. Quantum mechanics is formulated around a wavefunction, often denoted by the Greek letter psi. This psi describes probabilities, allows superposition, and collapses upon measurement. Our holophase foundation has only one fundamental field, phi. They are different Greek letters. Is psi just a rename of phi? Or is psi something that emerges from how we process information about phi? Can a single definite field give rise to the fuzzy probabilities and multiple possibilities of quantum theory without contradiction? The answer is a story of information, coherence, and constrained ignorance. It proposes that the quantum wave function psi is not the fundamental thing. It is a catalogue of knowledge, a compressed probabilistic description we use when we cannot track the full, intricate detail of the phi tapestry. But crucially, this catalogue is not arbitrary. Its rules, superposition, unitary evolution, collapse, are forced upon us by the geometric and topological structure of phi itself. Quantum mechanics is the user manual we are forced to write when interacting with the holophase universe. Let's build this from the ground up. We start with our single, continuous, cyclic field phi. At the microscopic scale, phi is not a placid lake. It is a turbulent, foaming sea of activity. Its value and derivatives are in constant, rapid fluctuation. Not random noise, but complex, deterministic chaos, or highly structured turbulence at the Planck scale. We, as macroscopic observers embedded in this tapestry, cannot possibly track every ripple and eddy. It would be like trying to track the position and velocity of every molecule in the air to predict the sound of a symphony. It's impossible. Instead, we use coarse-grained variables. Now, imagine we want to describe a particle, like an electron. In the phi tapestry, this might correspond to a specific, persistent topological defect, a knotted, self-sustaining vortex-like structure, as we discussed for charge. But this lump is not sitting in a void. It is immersed in and interacting with the seething sea of microscopic phi fluctuations, the zero-point motions of the tapestry itself. We cannot pinpoint the defect's exact instantaneous location and motion because its boundaries are fuzzy, dancing with the sea. So what do? We describe it statistically. We define a wave function, psi. This psi is a complex number at each point in space. Its magnitude squared gives the probability density of finding the particle lump there if we perform a coarse, disruptive interaction, a measurement. Its phase, the cyclic angle of the complex number, is of paramount importance. This phase is directly tied to the holophase itself. It is a coarse-grained record of the integrated cyclic changes of phi in the region associated with the lump. The phase of psi echoes the phase of phi. This connection is key. Because phi is cyclic and its phase matters, the derived psi inherits this property. This leads directly to superposition and interference. In the phi sea, a particle lump does not have to be in one narrow channel. The conditions that sustain it could be satisfied along multiple distinct paths through the tapestry, like a stable whirlpool that can form in one of several basins. The full phi state includes activity along all these possible basins. Our coarse-grained description psi must therefore be a weighted sum of the wave functions for each possible path. This is superposition. Psi equals pi path 1 plus psi path 2. When these possibilities recombine, their phases, derived from phi's phase along each path, interfere. If the phases align, the probability amplifies. If they cancel, the probability vanishes. This is the source of the famous double-slit interference pattern. It is not a mystery. It is the statistical shadow of Phi's phase coherent structure exploring multiple consistent configurations. So here is the point. Superposition is not the particle is in two places at once. It is the Phi configuration supporting particle-like behavior is coherently spread over multiple spatial structures, and our probabilistic summary psi must reflect that. Now, what about measurement and collapse? This is the hardest part. In our framework, a measurement is not a magical act. It is a specific, strong, irreversible interaction between the Phi pattern we call the system, for example, an electron lump, and another, vastly larger and more complex Phi pattern we call the apparatus or environment. This interaction is designed to amplify a microscopic detail, like which path the lump took, into a macroscopic recordable difference, like a pointer moving or a flash on a screen. Before the interaction, the system's Phi pattern is in a coherent superposition relative to the apparatus. The apparatus's Phi state is entangled with it, but the apparatus itself is made of billions of interacting Phi fluctuations. The interaction causes the microscopic superposition to rapidly decohere. The phase correlations between the different branches of the Phi tapestry get scrambled and lost into the inaccessible details of the environment sea. From our coarse-grained perspective, having lost track of those phase relationships, we can no longer use the interference-capable wave function psi. We must update our catalogue of knowledge to reflect that one branch has been actualized in our perceptual reality. This update is the collapse of the wave function. It is not a physical process hitting the fundamental Phi. It is a change in our information about which coarse-grained branch we are now correlated with. The other branches don't vanish. They become informationally separated from us. The Phi tapestry itself always evolves deterministically. This leads us to entanglement. Imagine two electron lumps created together from a common Phi process, like two vortices spawned from the same swirl. Their Phi structures are born correlated. Their individual phases are not independent. They are locked together. Even if these lumps are separated, the relationship between their phases persists in the global Phi state. Our coarse-grained description for the pair cannot be written as two independent psis. It must be a joint wave function that describes the correlated pair. This is entanglement. Measuring one lump forces a branch selection that immediately determines the possible outcomes for the other, because the measurement picks out a branch of the global Phi tapestry in which the correlation is manifest. There is no spooky action at a distance. There is only the revelation of a pre-existing correlation written into the shared Phi history. Let's explore the tri-unity of quantum phenomena emerging from Phi. The time echo of quantum mechanics, unitary evolution. When we are not performing measurements, our knowledge catalog psi evolves smoothly and deterministically according to the Schrödinger equation. This is the time echo, the continuous, predictable flow of phase. This evolution is derived from the underlying deterministic evolution of the full phi field under its action principle. The Schrödinger equation is an effective equation for the coarse-grained, complex amplitude psi, the space echo of quantum mechanics, the probability cloud. The electron in an atom does not orbit like a planet. It exists in orbitals, fuzzy clouds of probability. This is the space echo, the stationary, shaped distribution of where the phi pattern supporting the electron is most likely to be found. The shapes, spheres, dumbbells, cloverleaves, are determined by standing wave solutions of the Schrödinger equation in the atom's potential, which themselves come from the effective potentials generated by other phi structures, the nucleus. The motion echo of quantum mechanics, quantization. Energy, angular momentum, and other quantities come in discrete lumps, quanta. This is the motion echo, the discrete steps of change. Why? Because the phi patterns that are stable and persistent, like standing waves in a cavity, must have wavelengths that fit properly. Only specific resonant frequencies, energies, and winding numbers, angular momenta, are allowed by the topological and boundary conditions of the phi-tapestry. The condition for a stable, coherent lump is a quantization condition. Now, let's locate this deep synthesis on the master tree. This is the third and perhaps most intricate node of Book 9.9. The quantum mechanics synthesis node depends profoundly on everything that came before, on waves and interference, Book 9.3, on topological defects as particles, Book 9.2, on the action principle for dynamics, Book 9.4, on hierarchical coarse graining, Book 9.6, and on self-reference and measurement as interaction, Book 9.7. It enables the final synthesis of general relativity, as uniting quantum theory with gravity is the great unsolved problem. This node is the uncertainty principle of the tree itself. It defines the limits of our knowledge about the tree from within the tree. To grasp this, let's light lanterns from domains where blurred information and correlated knowledge are natural. A near lantern from a detective reconstructing a crime. The detective has evidence, a footprint, size 10, a witness who saw a tall person, and a dropped glove. From this, she constructs a probabilistic description, a superposition of possible suspects. Mr. A, tall, size 10, has a high probability amplitude. Mr. B, short, size 10, has a lower one. Miss C, tall, size 7, has zero amplitude, excluded. This mental wavefunction is a catalogue of her knowledge based on available coarse evidence. When she finds a definitive fingerprint, a measurement, the wavefunction collapses. Mr. A's probability becomes 1. The others become 0. The reality of who committed the crime was always definite, the fundamental phi history, but her description of it was probabilistic and updatable upon new information. A middle lantern from a vast, synchronized dance performance. Think of a stadium show with thousands of dancers. From your seat, you cannot see every dancer's face. You see patterns, waves, shapes, colors moving. Your description is in terms of these collective, coarse-grained variables. Two dancers on opposite sides of the field are entangled. If one moves left, the other moves right, according to the choreography, the global script. Your knowledge of one tells you about the other. The underlying reality is the precise motion of each individual, the phi state. But your workable description is in terms of correlated patterns. If a camera focuses on one dancer, a measurement, you lose sight of the full field pattern, the coherence, but you gain precise information about that individual. A far lantern from the history of quantum theory itself. In the early 20th century, phenomena like the photoelectric effect and atomic spectra forced a new grammar. Planck, Einstein, Bohr introduced quanta. De Broglie proposed matter waves. Schrödinger wrote his equation for psi. But the meaning of psi was debated. The Copenhagen interpretation, led by Bohr, essentially said, psi is a catalogue of our knowledge. Don't ask what's happening behind the scenes. The pilot wave theory of de Broglie and Bohm said, there is a definite particle guided by a pilot wave, a psi field. Our holophase synthesis takes a third path, closer in spirit to the psi epistemic view, psi as knowledge, but with a crucial difference. The thing we are ignorant about is not hidden variables in Newtonian space, but the exact microstate of the single non-Newtonian entity, phi. And the rules governing our ignorance are dictated by phi's own geometry. What is the specific language role of quantum mechanics within Holophase? It is the probabilistic grammar of inquiry. It is the set of rules that dictate how to form questions, observables, how to calculate the probabilities of answers, Born rule from phase interference, and how to update our knowledge when we get an answer, collapse via decoherence. It is the user interface for interacting with the phi universe when you cannot access its source code. The core question this part asks about phi is, does the geometric and topological structure of phi, when coupled with the unavoidable coarse graining of any finite observer, necessarily impose the calculational rules of quantum probability theory, superposition, interference, entanglement, and wavefunction collapse, as the correct method for predicting outcomes of experiments? We are moving from asking how phi writes deterministic stories to asking how it writes stories that look probabilistic to beings within it. What does this synthesis do? It demystifies the wavefunction, framing it as a tool for handling ignorance about complex phi details, not as a physical wave. It explains why quantum rules have their specific non-classical form. They are the rules of inference for a cyclic, holographically constrained field. It provides a natural origin for decoherence and collapse within a deterministic underlying framework. It unifies the quantum and classical worlds. Classical mechanics emerges when the phi patterns are so robust and localized that decoherence is instantaneous and superposition is negligible. Now, stability and change. This quantum synthesis holds in the regime where our coarse graining is appropriate, the microscopic world and its interplay with macroscopic apparatus. It would break down if we could somehow track the exact microstate of phi. In that God's eye view, the universe would be perfectly deterministic, and quantum randomness would be revealed as deterministic chaos. But for any observer within the tapestry, the quantum rules are inescapable. They are stable because they are forced by the logic of information access. This brings us to the rigorous falsifiability thread. This is not philosophical hand-waving. The claim makes concrete, testable predictions. The prediction spine. The phi grammar, when used to compute effective coarse-grained descriptions, must reproduce 1. Interference patterns, the double-slit pattern and its variants. 2. Discrete energy levels, the quantized spectrum of atoms, molecules, and confined systems. 3. Bell inequality violations, the specific, non-classical correlations of entangled particles up to the maximum quantum bound, the Zerelson bound. 4. Contextuality, the fact that the outcome of measuring one property can depend on what other compatible property you measure simultaneously, a hallmark of non-classical probability. Furthermore, because it is a specific phi model and not just general quantum theory, it should, in principle, make new predictions. For example, it might predict subtle deviations from standard quantum predictions in extreme regimes. For example, at the overlap of strong gravity and quantum effects, or in certain nonlinearities, or impose new constraints on allowed quantum states based on topological consistency. The fail condition, falsification. 1. Hollow reduction. If the only way to get quantum mechanics from phi is to artificially insert the complex numbers, the Born rule, and the collapse postulate by hand into the phi definition, the reduction is hollow. It must derive these features from simpler phi principles. 2. Failed reproduction. If a phi model, worked out in detail, fails to reproduce one of the core quantum predictions listed above. For example, if it predicts a double-slit pattern with no interference, or Bell correlations that are weaker than the classical limit, it is falsified. 3. Ruled out deviation. If the phi model makes a specific, testable new prediction, for example, a tiny violation of the Zerelson bound, or a specific energy level shift in a high-precision atomic clock, and that prediction is conclusively ruled out by experiment, that specific phi model is falsified. Let's design a measurement scene that gets to the heart of quantum strangeness. A concrete, high-stakes measurement scene, testing phi-derived entanglement with a Bell test. We don't just simulate a quantum computer. We build a system from a phi principle that should generate entanglement and perform the gold standard test. The system. A carefully engineered condensed matter system, like a pair of coupled quantum dots or defects in a diamond lattice, and V-centers, whose effective low-energy physics is explicitly derived from a fundamental phi model Lagrangian. The derivation must show that the two subsystems, the spins of the dots' defects, have an entangled ground state described by a specific maximally entangled wavefunction, like a singlet state. We separate the two subsystems, physically or in terms of addressability, and perform a Bell test. We randomly and independently choose measurement settings, angles, for each subsystem and record the correlation between their outcomes, for example, spin up or down. We collect statistics over many runs. The quantum prediction, standard QM. The measured correlations will violate the Bell inequality, demonstrating non-classical entanglement. The maximum possible violation has a mathematical upper limit called the Tyrrell-Sand bound. The phi model prediction. The derived effective theory for the subsystems must not only predict violation of the Bell inequality, but it must also predict that the degree of violation saturates exactly at the Tyrrell-Sand bound for a maximally entangled state. Furthermore, the detailed functional form of the correlation as a function of the measurement angle difference must match the cosine curve predicted by quantum mechanics. The pass condition, synthesis holds. The experimental data shows a clear violation of the Bell inequality, with the correlation curve and maximum violation matching the Tyrrell-Sand bound limited quantum prediction. This confirms that the phi model has successfully generated genuine, non-classical entanglement as observed in nature. The fail condition, synthesis fails. The data shows either A, no violation of the Bell inequality, the world is classical at this scale, or B, a violation that exceeds the Tyrrell-Sand bound, pointing to superquantum correlations not allowed by standard QM, falsifying the specific phi model's derivation, or C, a violation with a different functional form than the quantum cosine curve. Any of these would be a severe blow, showing the phi model does not reproduce one of the most distinctive features of quantum reality. This is the crucible. Quantum entanglement is not a mild effect. It is a sharp, mathematical dagger that kills classical hidden variable theories. Our phi framework must be able to forge and wield that same dagger. Let's cultivate a practical recognition skill. You can train your mind to see quantum-like reasoning in everyday situations where information is incomplete and outcomes are contingent on the act of inquiry. Look for context-dependent knowledge. Consider a jury deliberating a verdict. Before the final vote, the jury's collective state is a superposition of guilty and not guilty. Different lines of questioning, measurements, during the trial can change the amplitudes. The final vote is a collective measurement that collapses the superposition into a definite outcome. The process is not random. It's the resolution of a complex, informationally entangled state. Watch a person making a difficult decision. They hold multiple options in mind, weighing pros and cons, a superposition of futures. Discussing it with a friend, an interaction, can decohere the superposition, causing one option to crystallize as the choice. The act of asking for advice changed the outcome. Analyze a detective's suspect list, as before. The probability assigned to each suspect is contextual. It changes if the detective learns new information about the weapon or the motive. The probabilities are not properties of the suspects alone, but of the suspect information complex. Whenever you see probabilities that are not just due to ignorance of hidden dice, but that change in a non-commutative way based on what you choose to ask, you are seeing a shadow of quantum contextuality. We must connect this quantum synthesis directly to the core of the Holophase vision. We have added no new ingredients, no wavefunction on configuration space, no collapse postulate, no observer consciousness. We have only used the grammar we already built, a single, cyclic, deterministic field phi whose microstate is too complex to track, forcing us to use a probabilistic, phase-sensitive description, psi, when making predictions. The bizarre features of quantum theory, superposition, entanglement, collapse, are revealed as the natural consequences of doing statistics on a system whose fundamental degrees of freedom are not point particles, but the phases and topological structures of a universal field. The language role of this synthesis is the metagrammar of prediction. It tells us how to use the fundamental phi grammar to make testable forecasts when we, as parts of the grammar, are inherently limited in our perspective. What does this synthesis do for our understanding of phi? It completes its explanatory power. If phi can generate the quantum world, then it is a language capable of describing all of known physics, from the deterministic to the probabilistic. It shows that quantum weirdness is not a bug in reality, but a feature of its deep unity. Now, let's sound the tri-unity refrains for the quantum dialect. The time echo of synthesis, the unitary flow of knowledge. The time echo is the relentless, smooth evolution of the Schrödinger equation. the updating of our probabilistic knowledge catalog in the absence of new data. It reflects the underlying deterministic flow of phi. The space echo of synthesis, the entangled network. The space echo is the non-local correlation matrix of the universe. It is the realization that the psi for the whole is not built from independent psis for the parts. Space is filled with the ghostly threads of phase correlation, the entanglement structure, which is a direct imprint of phi's non-separable global state. The motion echo of synthesis, the quantum leap. The motion echo is the discontinuous jump of a measurement outcome. It is the sudden, unpredictable to us, transition from a spread of possibilities to a single actualized record in our branch of the phi-tapestry. It is the moment our knowledge catches up, with a click, to a particular thread in the weave. This is where we stand on the master tree. The quantum mechanics synthesis is the luminous, fragile fruit on the highest branch of book 9.9. It is the point where the tree's self-reference becomes most acute. The grammar generating observers who then use a probabilistic shorthand to describe the grammar itself. Its success means we have not just unified physics, we have begun to unify physics with the process of knowing. If you want to see the full mathematical derivations and exact equations behind this idea, the formal coarse graining from phi microstates to a density matrix, the derivation of the Born rule from phase averaging, the emergence of decoherence from phi interactions, the derivation of the Zirelsen bound from phi topology, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. We have translated the third great epic. The mysterious quantum world is not a separate realm with alien rules. It is the world of phi, seen through the lens of a participant. The collapse of the wavefunction is the turning of a page in the book we are writing about ourselves. Our journey in book 9.9 has one final monumental synthesis remaining. We have seen phi generate the mechanics of the small, quantum, and the forces of light, electromagnetism. But there is a force that shapes the cosmos itself, the geometry of space and time, gravity. In the next part, we will see how phi writes the stories of general relativity. Before we end, the mandatory zoom out to hold our scope. Quantum mechanics as a phi dialect shows that probability and wavefunction collapse are not primitive. They are grammatical constructs, epistemic tools, and update rules, in a story whose only fundamental reality is the deterministic complex field phi and its complete history. One field, phi, plus its infinite derivatives, plus the recognition that any internal observer's knowledge is a coarse-grained probabilistic summary of that derivative structure. From this, the entire bizarre, beautiful, and empirically flawless edifice of quantum theory emerges. We have not explained away the mystery. We have relocated it from the laws of nature to the nature of our participation within it. As we conclude, hold the image of the scribe and the blurred manuscript. He does not despair at the smudges. He understands that the smudges are part of the text. His transcription into clear probabilistic script is the only honest way to copy it. The Holophase universe is that manuscript. Quantum theory is that faithful transcription. And we, as conscious knots within phi, are both the scribes and the readers, discovering that the story of the universe is ultimately the story of how it knows itself. Salam, and peace be upon you.